Every time you send an email, you participate in a miracle. When you stream a video, you command an invisible empire. When you make an international call, your voice travels through the deepest, darkest places on Earth. Our modern world is built on instant, global communication. We see it as wireless, ethereal data in the cloud. But this is a profound illusion. 99% of all international data does not travel through the air. It is not beamed from satellites. It travels through a physical network of cables. These cables lie on the cold, dark floor of the world's oceans. This is the real internet. A planet-spanning web of glass and light. It is one of the most critical pieces of infrastructure ever built. Yet it remains almost completely unseen. Its story is one of impossible engineering. It's a story of audacious ambition. And it's the story of a secret battle for control. A battle that began over 150 years ago. And it continues to this day. This is the blueprint for the physical backbone of our digital world. It is the 1850s. The world is vast and disconnected. An urgent message from London to New York travels by steamship. The journey takes weeks. Empires are built and lost in the time it takes for a single order to cross the Atlantic. But a new technology is spreading across the land, the electric telegraph. Messages travel through copper wires at nearly the speed of light. It connects cities. It transforms nations. Then, a truly radical idea emerges. An idea bordering on madness. What if a telegraph wire could be laid across the entire Atlantic Ocean? This was a challenge of unprecedented scale. The ocean was a terrifying, unknown abyss. It was over 3,000 kilometers of crushing pressure and jagged underwater mountains. No one had ever laid anything of this length at such a depth. The cable itself was a marvel of its time. A core of 7 thin copper wires. This was the conductor for the electrical signal. It was insulated with a strange, natural plastic called gutta percha. This material, derived from a Malaysian tree, was the key. It was the only known substance that was truly waterproof and could withstand the deep ocean. This insulated core was then wrapped in tarred hemp. Finally, it was armored with a sheath of thick, interlocking iron wires. The final cable was heavy, thick, and brutally expensive. American financier Cyrus Field was the man possessed by this vision. His first attempt in 1857 failed. The cable, weighing over a ton per mile, was too heavy. It snapped under its own weight and was lost to the sea. His second attempt also failed. A storm battered the ships, and the cable broke again. Critics called him a fraud. The public derided the project as a fantasy. But Field was relentless. In 1858, 2 warships, the HMS Agamemnon and the USS Niagara, met in the mid-Atlantic. They each carried half of the precious cable. They spliced the ends together. Then, they sailed in opposite directions, slowly unspooling their cargo into the deep. Against all odds, they reached their shores. The cable was connected. On August 16, 1858, the first message traveled from Queen Victoria. It was sent to U.S. President James Buchanan. The 98-word message took over 17 hours to transmit. The signal was incredibly weak. Engineers tried to boost the voltage. This was a fatal mistake. They effectively fried the delicate insulation. After just 3 weeks of sporadic use, the cable went silent. The dream had failed. It took another 7 years and a civil war before Field tried again. This time, he used a single, colossal ship. The SS Great Eastern was the largest vessel in the world. It was a true iron behemoth. It carried the entire, improved, 5,000-kilometer cable in its hold. In 1866, the Great Eastern successfully laid a new, durable cable. The world was now permanently wired. Continents were linked in minutes, not weeks. This was the birth of the global communications network. By the mid-20th century, the world had changed. The telegraph was no longer enough. People wanted to transmit the human voice. The age of the telephone had arrived. But sending a voice signal across an ocean was a new impossibility. A telegraph signal is simple, a binary pulse of on or off. A voice signal is a complex, analog wave. Over long distances, this wave degrades into useless noise. On land, amplifiers called repeaters could boost the signal every few kilometers. But how could you place a repeater on the ocean floor? How could you power it? And how could you build it to work flawlessly for 20 years? Any failure would require an impossibly difficult deep-sea repair. Engineers at Bell Labs took on the challenge. Their solution was the L3 coaxial cable system. The repeater was a masterpiece of durable engineering. It was a flexible, articulated steel cylinder, 2 meters long. Inside, 3 delicate vacuum tubes, the ancestors of the transistor, did the work. Every component was tested to destruction. Every solder joint was inspected by hand. These repeaters were designed for a 20-year lifespan, buried under 4 kilometers of water. In 1956, the first transatlantic telephone cable, TAT-1, was laid. It was a joint project between the US, UK, and Canada. It was an instant, overwhelming success. It could handle 36 simultaneous phone calls. In its first year, it carried over 300,000 calls. This was a major strategic asset during the Cold War. It provided a secure, instant link between world leaders. It was a hidden artery of power, far from Soviet ears and spy satellites. Over the next 30 years, more coaxial cables were laid. Capacity grew with each new generation. TAT-7, laid in 1983, could handle 4,000 calls. But a new storm was gathering. A digital tsunami called the Internet. And the old copper world was about to be completely washed away. The Internet was fundamentally different. It wasn't about a few thousand voice calls. It was about data. Potentially infinite amounts of data. Coaxial cables, with their limited bandwidth, were a bottleneck. A new technology was needed. Something with near limitless capacity. The answer came from a surprising place: pure glass. Fiber optic technology was a radical concept. Data wasn't sent as electricity through copper. It was sent as pulses of light through a strand of glass as thin as a human hair. The challenge was making the glass pure enough. Early optical fibers were so impure, the signal faded after just a few meters. Scientists at Corning Glass Works achieved a breakthrough. They developed a process to create glass so transparent that if the ocean were made of it, you could see the seafloor. The second challenge was building the lasers and receivers. They had to be tiny, reliable, and able to work for decades under the sea. The result was the first transatlantic fiber optic cable, TAT-8. It was laid in 1988. Its impact cannot be overstated. TAT-8 could carry 40,000 simultaneous conversations. More data than all previous copper cables combined. This was the inflection point. This was the technological spark that allowed the World Wide Web to explode. Suddenly, there was enough bandwidth to connect the entire world. The blueprint for the modern internet was now complete. A modern undersea fiber optic cable is a deceptive object. On the outside, it's a simple, rugged tube, about the thickness of a garden hose. But its inner layers tell a story of extreme engineering. At the very center are the optical fibers themselves. Dozens, sometimes hundreds, of hair-thin glass strands. Each capable of carrying terabits of data per second. These are protected by a copper sheath, which carries high-voltage electricity. This electricity powers the optical amplifiers, or repeaters, spaced every 70 kilometers. These are the modern heirs to the old vacuum tube repeaters. But instead of amplifying electricity, they use lasers to re-energize the light pulses. Wrapping these layers is a polycarbonate shell. Then, a sheath of steel wires for strength. And finally, a tough polyethylene jacket for waterproofing. In shallow water, near the shore, extra layers of steel armor are added. This protects the cable from anchors, fishing trawlers, and even shark bites. Laying this cable is a precise, 24/7 operation. Specialized ships, costing hundreds of millions of dollars, carry the cable. They use GPS and dynamic positioning to stay perfectly on course for weeks at a time. A deep-sea plow is often used. It's towed behind the ship, carving a trench in the seabed. The cable is fed directly into this trench and buried for protection. This invisible network is owned and operated by a complex web of players. Historically, cables were built by consortia of telecom giants. Companies like AT&T, Vodafone, and Orange would pool billions of dollars. But in the last decade, the game has changed. A new set of players has entered the arena. Google, Meta, Amazon, Microsoft. These tech titans now consume more bandwidth than entire countries. They can't afford to be dependent on the old telecom consortia. So they started building their own private cables. Google's Do Not cable connects Virginia to France. Meta's 2 Africa cable will encircle the entire African continent. This is a new, secret battle for the bottom of the ocean. Controlling the cable means controlling the flow of data. It means speed, reliability, and a massive strategic advantage. The choice of a cable's landing point is a major geopolitical decision. A country with many landing sites becomes a digital hub. A nexus of data, finance, and power. Countries with few connections risk being left behind in the global economy. But this critical infrastructure is also fragile. Cables can break. An anchor drop, an earthquake, or a deep-sea landslide can sever a connection. When this happens, a very special operation begins. A repair ship is dispatched to the location of the break. It deploys a remotely operated vehicle, or ROV. This deep-sea robot descends into the blackness. Guided by pilots on the ship, it finds the buried cable. It uses high-pressure water jets to expose it. A powerful cutter snips the damaged section. The ROV then attaches a grapnel to one end of the cable. This end is painstakingly winched up to the surface. The process is repeated for the other end. On board the ship is a hyper-clean, specialized laboratory. Technicians, working like surgeons, strip back the cable's layers. They face the final, delicate task: splicing each individual glass fiber. They align the two hair-thin ends perfectly. A machine then fuses them together with an electric arc. Once all fibers are spliced and tested, the repaired section is sealed. It's carefully lowered back to the seafloor. The entire process can take over a week. It is a testament to the hidden, human effort required to keep our digital world running. From the first spark of a telegraph signal, to the torrent of light in a modern fiber, this network has been the driving force of globalization. It is an empire of glass, buried in the dark. A silent, ceaseless battle for bandwidth and control. It's the single greatest piece of infrastructure we've ever built. And it's the one we never see.